Okay, so I am Harish Krishnani. I am a PhD student at ISER Mohali. So I am conducting your live interaction session for this Algebra 1 course on each Friday from 6 to uh, uh, 7 or 7:30. And so we have already discussed assignment 9 uh, of the last year course. Today we are going to discuss assignment 10. So let us start. Assignment 10, 2021. And this is part of week 10 in live interaction session. Okay, so let me paste the first question. So it says, consider the Z module m equal to z square. Which of the following maps are automorphisms of this module? So there are four options available. First option is f is mapping the tuple x comma y to x plus y to x plus y. Second says that fxy is minus of y comma x, and third is fxy is 17x plus 3y and 11x plus 2y, and the last one is 2x plus y 3x plus 3y. So we need to see that which of them are automorphisms. So as all of these functions are linear functions in coordinates, so all of them are going to be homomorphisms. So I'm just going to write it. So the solution is all these functions are coordinate wise linear. So all of them are homomorphisms. Homomorphisms. Right. Now we need to check that which of them are automorphisms. So let's first see the first one, that is f of x comma y is x plus y 2x plus y. Okay, so we will see first whether it is injective or f is 1 1 or not. So for that, what we will do, mm, we assume that for two elements f has the same image. Now that will imply that x1 plus y1 2x1 plus y1 is same as x2 plus y2 2x2 plus y2, and comparing them coordinate wise, you will get x1 plus y1 is same as x2 plus y2, and 2x1 plus y1 is same as 2x2 plus y2. So now from here, how can you conclude that mm, x1 is same as y1 and x2 is same as y2. So see, this equation will imply that x1 minus x2 is y1 y2 minus y1, and this will implies that 2 times x1 minus x2 is same as y2 minus y. And when you combine them, this equation with this equation will give you 2x1 minus x2 is same as x1 minus x2, and that will tell you that x1 minus x2 is 0, and thus x1 is equal to x2. Okay, now put them in any one of the equation. This is your first equation, say, and this is your second. So now from first one we will get uh, z- 0 is equal to y2 minus y1, and that will imply that your y1 is also same as y2. So this implies f is 1 1. Now the second mm, thing is to check that whether f is uh, also surjective. If it is surjective, then it will become a automorphism. Otherwise, it will just be a injective homomorphism. The next thing is to check that whether f is surjective. And how to do that? So let's start with an arbitrary tuple. Let alpha beta belongs to z square such that f of x comma y is alpha beta. Then what you need to do, you need to find some uh, x and y. You need to find the pre-image of alpha and beta. But if f of x y is alpha beta, then you will have x plus y, 2x plus y, same as alpha beta, because f of x y is given to be uh, your x plus y, 2x plus y, right? And that will imply that your x plus y is alpha and 2x plus y is beta. This is your equation first and this is your equation second. So what you do, you just do second minus first. That will give you x is same as beta minus alpha. Then put it back in 1. You will have beta minus alpha plus y is your alpha, and that will imply that your y is 2 alpha minus beta, right? And thus for all alpha beta in z square, there exists beta minus alpha and 2 alpha minus beta inside z square, such that f of beta minus alpha to alpha minus beta is alpha beta, right? And that will imply that f is surjective, and combining all these we have f is a automorphism. Now this is for the first function. So first is a correct option. Now for the second one, xy going to minus yx. Now you need to see for second one, fxy is minus y comma x. So one we need to check first. So how we can do that? F of x1 y1 equal to f of x2 y2 implies minus y1 x1 is equal to minus y2 x2, which implies y1 equal to y2 and x1 equal to x2. Thus your x1 y1 is same as x2 y2, and which implies f is 1. Now on to for on to thing, what you need to do, that for all uh, alpha beta in z square, they adjust beta minus alpha in z square such that f of beta minus alpha is minus of y minus of y, that is alpha, minus yx, that is alpha beta, and this implies f is onto, and hence f is an automorphism. So the first and second one we have checked. Now it's time for the third one. So let's see the third example. So it says 17x plus 3y. It is here you have third option is f of xy to be 17x plus 3y, and then you have 11x plus 2y. 11x plus 2y. Now what you need to check first, that it is 1 1. For 1 1 you have 17x1 plus 3y1. If uh, say f of x1 is same as f of x1, f of x1 y2 is same as f of x2 y2, then what will happen? We will have this kind of condition, and this is equal to 17x2 plus 3y2, 11x2 plus 2y1, oh, sorry, 2y2. Now compare the two coordinates. This will imply that mm, your mm, 17x1 plus 3y1 is same as 17x2 plus 3y2, and 11x1 plus 2y1 is same as 11x2 plus 2y2. Okay, so from here you have 17x1 minus x2 is same as 3 times y2 minus y1. Let it be equation 1. And here you have 11x1 minus x2 is same as 2 y2 minus y1. That is your equation 2. Now what you can do, uh, 2 times 1 minus 3 times the second equation, or let us write it in Romans to avoid the confusion. So let this is equation first, this is equation second. So do 2 times 1 minus 3 times the second equation. That is, to multiply it by 2, this will be 34 x1 minus x2 minus 33 x1 minus x2, and will have it to be 0 to the other side, and that will imply that x1 minus x2 is 0. That will give you that x1 is same as x2. Putting it back into the first one, we will have that 0 is same as 3 times y2 minus y1, and that will give you y1 is same as y2. Okay, so, and this will implies that this is 1 1, f is 1 1. Okay, so, and similar to part 1 and 2, one can check that f is on 2 as well. Now for the fourth one, you have f of xy to be 2x plus y, 3x plus 3y, 2x plus y, 3x plus 3y. F of xy is 2x plus y, 3x plus 3y. So uh, there is a twist in that, because this function won't be injective, or you can say, yeah, sorry, it is injective, but it won't be onto. I think for injectivity also there will be an issue, but at least it is not onto that, you can see, because clearly if you look at this, it is saying that it is 2x plus y 3 times x plus y. So this is always a multiple of 3, right? So that will implies that, say, f of xy cannot be 2 comma 1, because this is Not a multiple of 3. This is not a multiple of 3. So, right. So if it is not a multiple of 3, then definitely the function is not surjective. So first 3 are correct, and you will have a problem when you will try to check the fourth one. Okay. So first, second, and third are automorphisms, but the last one is not. Okay, then. Yeah. So let's move to the next question. Yeah, here it is. So it says for a Z module Zn, where n is greater than equal to 2, you need to check whether the following statement is true or false. That a map f from Zn to Zn is a Z module homomorphism if and only if it is of the form f of x1, x2, xn, linear sum of xi's in each coordinate. So see, we will go first see, let's say the forward implication is correct. We will first check that if it is an homomorphism, then what can you say about it? Okay, so it's saying that if it is a homomorphism, then it is of it is of the form this, or maybe we can go simultaneously, right? So first of all, as in a you are in a module, so only addition and multiplication is defined. You don't have the uh, concept of inverse in general. In fact, as your ring is Z, so you don't have the inverse for each element. So you cannot say that a homomorphism is a rational function. It's going to be a polynomial function in general. So if f is a homomorphism, or let me just give some more details. If f from Zn to Zn is a Z module homomorphism, then f has to be of this form. Okay. Hmm. I should write it more clearly. Some p1 of x1, xn, p2 of x1, xn, and then you have pn of x1 dot xn, right? Now, what else uh, you can say? mm, even JAD module, mm, just a module map. We're just defining a map. Then map has to be some polynomial because in modules you don't have the concept of any other function. You just know that it's a module. Uh, so only polynomial functions are well defined. Now, if uh, pi has a constant term, then pi of this x1 comma xn plus you have y1 comma yn, then that would be equal to your pi of x1 comma xn plus pi of y1 comma, right? Because here you will have a single constant term and here the constant term will be added twice. So that won't be the case. Okay. And this will contradict that f is a homomorphism. So we are in the forward implication. Uh, Now, also if any of the pi has a higher uh, order term, then also the same problem will higher degree term or order term that it is same. Then also the same problem will arise that you can't separate out. Then this won't be linear, right? Because to respect the linearity, you must have the linear polynomials. This will implies to preserve f is not a homomorphism, and that means that to preserve linearity, each coordinate must have linear polynomials with constant term with zero constant term. Okay. Yeah, and that will imply that your f is of the given form 2 1 to n of x1 to xn. This will implies that f is x1 to xn summation of I equal to 1 to n a1 I xi dot 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 summation of I equal to 1 to n a n I xi. Okay, so yeah, this is what we were supposed to show. Now the other part, okay, the other part is quite easy because as each of the coordinate have as each coordinate has linear polynomials with zero constant, therefore f has to be a homomorphism. Okay, so mm, you have that each polynomial is a is function each coordinate function is a linear polynomial with zero constant, so it's going to be a homomorphism because it will respect the linearity, and thus the statement is true. Okay, so now let's move on to the third question. So it says true or false. Let R be a ring not necessarily commutative. The endomorphism ring of R is isomorphic to the matrix uh, ring as rings. So both of them are ring homomorphism where if R is not necessarily commutative. So the statement is false since endomorphism ring of R is isomorphic to matrix ring of R only if R is commutative. For non-commutative ring, you won't have this because um, if you look at the proof, how we prove this Rn is isomorphic to matrix ring of R, then to interchange the coordinates, we need that R has to be commutative. Uh, in the first lecture of this week, it has been proved that this ring is isomorphic to matrix ring of R. There we need that R has to be commutative. Then only we can interchange the coordinate, the scalars, and for that, without that, we won't be able to show that. So that's why this statement is false. Mm, or I think I should write it like this. If R is commutative, but in general we don't have this relation. Okay, so let's move to the next question. It says, let R be a ring not necessarily commutative and n greater than equal to 1. Consider the following statements. Uh, if R f from Rn to Rn is a surjective module homomorphism, then f has to be injective. And if f from Rn to Rn is a injective module homomorphism, then f has to be surjective. So you need to find examples whether uh, this thing is not holding, because this is not true in general. Okay, so first of all, I will just say I leave it to you guys to consider explicit examples, but you can check easily that A and B are false in non-commutative setup. And you need to see that why mm, it is not holding. Okay, try to consider explicit examples. If you have any problem, then we can uh, look at it in the next uh, live interaction session. Okay, so let me move on to the next problem. So it says, again a true false question. The following two statement is are equivalent or not. An R module M has a basis, uh, that is a set I belonging to the indexing set I of elements, uh, such that any M can be written as a product of as a linear sum of these EJs, and uh, the set of these EJs is finite. Okay, so that means you have a set EI corresponding to an indexing set I, and you can find a subset. Okay, okay, so I just uh, make it more confusing. So it says that R has a basis if they register set EI for an indexing set I, such that any element of the module can be written as a finite linear sum of these EJs. Okay, so that indexing set need not be finite; it can be an infinite set. But if you are considering one element at a moment, and it has to be the sum of finitely many elements from uh, the the set EIs. Okay, so it's just like you define the basis of a vector space. There also the dimension could be infinite, but uh, at a time when you're considering a particular element, it should be written as a finite sum of the elements. Okay, so now the second statement says that R is isomorphic to the direct sum of R over the indexing set A, where the direct sum of R over A denotes the R module consisting of sequences RAs. A is varying over A, okay, such that RA is 0 for all but finitely many A's. Okay, and over this you impose a ring structure as through the usual component addition and multiplication of elements. Okay, the module structure, sorry, not the ring structure. Now you need to see that whether these two statements A and B are equivalent or not. So let us try to see that. Mm, okay, so we will define a map phi from, okay, isomorphic to some, okay, so let's say, so let an R module M as a basis AI such that phi is from 1 to I is in the indexing set. Now you need to define a map to the direct sum over I. Okay, so from, okay, from M to the direct sum of R over I, we can define a map in the following manner. Let's say the phi map is this. Define as phi of M. Now this phi is, this M is a it can be written as a linear sum of these EJs, finite linear sum. Okay, and this representation is also unique. So let us write this as Rj Ej, and G is varying over M. G is varying over I. Sorry, G is varying over I. This is finite, or say unique representation. Maybe finite is already guaranteed. So unique representation of this small m. Now you just send it to the tuple or the sequence Rj. Send it to the sequence Rj. Okay, because each Ra is from each Rj is from ring, this ring, yes. So and j belonging to I, and here also you are given that only finitely many are non-zero, right? Because it's a finite linear sum. So that makes sense. As a map, it makes sense. You can check that. Now it is well defined, and also mm, this map is a homomorphism. You can just say check that it's a homomorphism. It's a homomorphism. Now we need to see whether the map is an automorphism. So for that, first claim is whether the given whether the defined map is 1 1 or not. If phi of m1 is equal to phi of m2, where m1 is say some rj ej j belongs to I, and m2 is some sk ek k belonging to I, then what will you have? You have these rj's is same as sk as a sequence, and that will implies that rj equal to sj for all j belongs to I. You can take the same indexing, no problem, because you need not to take the sum or anything. It's just a representation. So you can take the same indexing. Sj is a j is inside I. Now what will just a minute. Yeah. Yes. So this will implies that m1 is m2. So one is done. For on two also you can say uh, simply let rj j inside I be a sequence with rj's equal to 0 for all but finitely many of j. Okay, so we can simply take those for which rj's are not non-zero. Let j1 j2 soon to jk be the set of indices for which rj is non-zero, and let us term this index set to be j. Say say let J, which is this, be the set of indices for which Rj is non-zero, and Rj is zero for all J inside I minus this index inside. Now define M as R J. Define M to be the with this R J1 E J1 dot 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 R J K E J K, right? So you can take this element is inside your M, then phi of M, if you look at that, it will be your sequence Rj, right? So let name this, give some name to the sequence. Maybe what should be a good name, or let it be just some sequence alpha. So it is alpha again. So it will implies that phi is onto, right? So these two are isomorphic. Means the set is isomorphic to R. So M is isomorphic to our index inside this, right? So A implies B. This will clearly say that A implies B. Now, for the other part, this is the proof for A implies B. Now for B implies A. B implies A is going to be easy. Let's see how. B implies A. That your M is isomorphic to this R A of R. Okay. And just for the sake of writing it in a better way, let me write it like this. This is also same, right? I'm just want to give the homomorph or isomorphism from R to this. Okay, like this through the automorphism by the, sorry, not the automorphism, should be isomorphism by the isomorphism phi. Hmm. And let EI is the set. mm, you have 0 everywhere except at the, or let me write it in the form of a sequence because we are considering it to be elements of direct sum of R as a sequence. So It is a sequence Rj, J belongs to A such that Rj is 0 if J not equal to I, and Rj is 1 if J equal to I. So at the ith place you will have 1, and except this you will have 0. Let the Ei is this, and phi of Ei is Mi, which is inside, or you need not to write this as well. This is also fine. Now we claim that you can check that the set of all phi of Ei, I varying over A, is a basis of L. So these two statements are equivalent. Okay, so you have a true, this statement to be true, right? Now let us go to the next question. I will just copy it. Mm, Just give me a second. Yeah. So here is question number 6. It says that let M be a R module that has a basis even to EI, I from I is varying over the indexing set I. Then whether the statement is true or false. The statement is if the finite set M1 to Mk generates M, that is each element of M can be written as a linear sum of finite linear sum of these MIs, then I is a finite set. Okay, so yeah, what can you say about it? So M is an R module that has a basis EIs. So and each element of uh, M is generated by a finite set. So yeah, so what we can do, we can also use the previous statement or try to prove it independently as well. So clearly, mm, as there are just these sets, you can see that you can define the map homomorphism uh, define phi from M to the direct sum of over R, where the I is just 1, 2, and k, such that for any m, as m is inside m, it has to be the sum of some ai, mi, r is from 1 to k, and any inside m we have phi of m to be uh, or let us first define it for eis such that phi of okay mi is ei, that is a sequence rj, j belongs to I, such that rj is 0 if j not equal to I, and rj is 1 if j equal to I. So we define it for basis elements, and then we can extend it, uh, then extend phi in the following manner. So for any m which is a direct sum, which is a linear sum of these mi's, we have phi of m to be just summation of I equal to 1 to k ai phi of mi. So one can check that uh, phi is a homomorphism. Well, instead of just implies, I will say check that phi is a homomorphism. There is nothing much to be done, but still you need to check it. Check that phi is a homomorphism, and not only homomorphism. To the same process, we proved the equivalence of two statements in part one. You can prove that phi is in fact a isomorphism. Isomorphism. Okay. So now you have already seen that if by part second of the fifth question, that question fifth, if this kind of situation happens, then it implies that the underlying indexing set will give you the basis. From question 5, we uh, conclude, we can conclude that the set instead of uh, ei, let me write, because ei we are using it for basis elements, so it should be, let's say, some sequence alpha I. Okay, So we can conclude that ei I belonging to 1 to k, and that is precisely your oh. So we are just given that MIs are generating sets, right? So it will cover the entire R, because each element of R, just give me a second, it is surjective, it's going to be surjective, but need not be injective because we are not assuming the unique representation. So phi is an, you can say that it is an onto-homomorphism. Onto-homomorphism. Okay. So still some things needed to be done. So this will implies that M modulo kernel of phi is going to be isomorphic to this I equal to 1 to k over R. Right. Now, mm, you have a basis of this kernel of phi is going to be conclude that let me just think for a while. We define from M to R the following map, okay, and then corresponding to which you can get okay, it is undetermined this, so you will get this, no issues, it won't be, it won't be subjective or छोटा होना चाहिए. Oh, sorry, it is an injective map because each generator is being mapped to a sequence, and as these MIs varies, these sequences will vary. So mm, this is going to be an injective map. Injective homomorphism. Yes, I'm a bit confused here. So from M to R, you have a map such that Mi is being mapped to the sequences Ris, and you are considering it to be K. Now this is injective because each element M you can write it as MIs, sum of MIs, but that may not be the same. Yes, yes, yes. You may have more than one representation for an element M because it's not the basis. So, yeah, so it will uh, will give it will be a problem, because then you have more than one representation for a part, for a single element. Okay, so the problem is in the extension of this phi. This phi won't be uh, this phi won't be well defined. We can't extend it in this manner. So there is what we can do, but we can just define the converse map. So let me just change the things. Uh, See, the problem here is for mi you can define a unique element rj, but this sum is not unique. So you can also write it as summation of j equal to 1 to k bj mj, right? Because this is not a basis, this is just a generating set. So you may have more than one representation. So extending it like that will not give you a unique image for a single element. That's why the this map won't be well defined if you extend it like that. So it's better to define the converse map from here to here. So you have r here, or the direct sum of r. I is varying, I is just 1 to k, and that is from here to m. You can define it like that. But first you define it over ei's. Let me just rewrite the entire thing again. I hope you can understand the problem. The problem here is uh, from in M you don't have a unique representation of an element, but in R, in direct sum of R, you have a unique representation, because it's a direct sum, so it will be uh, generated by the alpha is where your al- alpha e has one only at ith place and zero elsewhere. So it is uh, it, it can be extended through mm, the basis element, because it has a basis. Define this R2M uh, such as phi of alpha j is mj for all j belonging to 1 to k. Or let me just write it I here, because we are varying over I. So mi where you have a specific uh, r representation of ra. This is just rj such that rj is 0 if j not equal to I, and rj is 1 if j equal to I. Now we can extend phi in the following manner. For any rj, or let us say sj inside, I will just rewrite it again to avoid any confusion. So for any sequence Sj inside your direct sum over R, where the indexing set is 1 to k, we have here you have the unique representation. The sequence Sj is just the sum of these uh, AI times alpha I equal to 1 to k, and for some AI is inside during R, uh, then phi of Sj is nothing but the summation of I equal to 1 to k AI of phi of alpha I. Okay, so what does this mean? This mean that you have a homomorphism from the direct sum of R to M, and this homomorphism is injective because for each element Sj you can write it uniquely as in the sum of Ai alpha I, and you have defined the map uh, on A alpha I, so this will be an injective map. Earlier we are not having this unique representation, so that the map we defined earlier was not injective. So phi is an injective, or I will just say that check that phi is an injective homomorphism, because still some checkings need to be done. Check that phi is an injective homomorphism. Once you have this, you uh, can say that this will implies that from direct sum of R I is 1 to k, you have an injective map. So the kernel of modulo the kernel of phi is isomorphic to M. We conclude that, and this R is a free module. The quotient of a free module is again a free module. That's something you need to check. So this will implies that direct sum of R, uh, you have some indexing set, say I1, I2, so on to IR inside I, and that sum is isomorphic to M, and from question 5 we have uh, mm, yes, so from question 5 we have corresponding element EI1 to EIR is a basis of, so you have got a finite uh, set uh, such that uh, finite you got a finite basis EIs of the M, right? Okay, so now let's move on to the next question. We'll just copy the question. This question is very interesting. Let us try to see. So R is an integral domain, and we are given a module M which is finitely generated, and we need to mm, uh, see whether the following two statements are correct. So for every finitely generated torsion R module, we have annihilator of M to be non-zero. So I will just give you some. idea about the torsion of M module and the annihilator of M. I hope you have already seen this definition, but if not, then uh, I will recall the definition for you, and then you can understand the question well. So let's move to the solution part. Okay, so M is a torsion R module if for each uh, M in M there exist some R depending on this M non-zero element inside R such that you have M times you have Rm dot M to be 0. Okay, now since you are given that it's a and let me write the definition of annihilator also. Annihilator of M. Annihilator of M is the set of all elements of ring R such that for all such that you have just R times M to be 0. Now let's go to the question. This is the recalling part, right? So we will now see the proof of the question statement A. So let's try to prove A. So you are given that M1, M2, Mk generates M. Okay. Now since M is a torsion module, that you are given, right? In part 1, M is a torsion R module. Since M is a torsion R module, uh, so uh, what we have, so for all Mi which is inside the generating set of M, we have for all Mi we have Ri belongs to R such that Ri Mi is 0. This is just by definition of your torsion module. Okay. So now let define R to be the product of these Ri's. Okay. Then we claim that R will be there inside. Uh, okay. So this is going to be non-zero since this Ri is non-zero, right? So we will have let R is this, then since your R is an integral domain, this is the place where we are using R to be an integral domain. Since R is an integral domain, R is non-zero, and for any uh, m belongs to M, you have R of M, that is R1, R2, so on to Rk of M, and before that uh, you also have this M is the M is generated by mi's, so from I equal to 1 to k you have a linear sum. You can write M as a linear sum of mi's, so you just need this thing also you have I is equal to 1 to k. Now you can split them as following: summation of I equal to 1 to k, you have R1 Rk ai times mi. Now since R is an integral domain, now since R is an integral domain, we have that it is commutative. It is commutative, and that will implies that R dot M is summation of I equal to 1 to k. Just take R1 so on to dot R I minus 1 dot R I plus 1 dot R k ai R M R I M I, but that part is 0, right? And that will implies that this R dot M is 0, and as your IM was an arbitrary element of M, this will imply that R belongs to any liter of M for all M belongs to M, and thus the intersection of uh, thus this R is inside the intersection of all annihilitors, and this is what we are supposed to prove, right? We need to show that this intersection is non-empty. So if R non-zero, sorry, not non-zero, uh, mm, yeah, no, it's non-zero. So R is there. This implies that this intersection uh, is uh, not equal to the zero, right? Yeah. So that's the first part. Second part says that we need to find an example, uh, because the second part is not true. Let me tell you. The second part says that there is just an R module M such that the annihilator is equal to 0 and M is equal to the torsion of M, collection of all elements. Uh, so torsion and of M is a collection of all elements for which this kind of condition is true. Okay. So we need to see an example. Okay, we need if the statement is not true, then we need to find an example. R module such that any liter of M is 0 and M is torsion is a torsion module. So what condition we don't have here? It's not given that it's finitely generated. So definitely we need to find an example. Uh, we For finding an example, we need to look for an infinitely generated module. So let me give you the example. So let your R is Z and M is the direct sum of Z modulo Z by 2 I of Z. So your it's not so your I is also increasing. So it's like Z modulo 2Z direct sum Z modulo 4Z direct sum Z modulo 8Z direct sum dot. It's an infinite uh, direct sum, right? So mm, now mm, we need to say that this is 0. So let uh, some element A belongs to M. Now if A is inside M, then A is like this: A1 plus Z times 2Z plus 1. So after a certain coordinate, you will have 0 everywhere, because uh, you can have only finitely many coordinates to be 0, as by the definition of direct sum. Dot ak plus z modulo 2k z, and then you have 0 0 dot 0 everywhere. Okay, so these ais belongs to z, and ais may be 0 as well for some I. Okay, so it's not necessary that these you will get non-zero, but after a certain k you will have 0, each coordinate to be 0, because you can't have infinitely many non-zero coordinates, right? So that's what I'm saying. But, after certain k you will have 0 everywhere. Now uh, this you can say that person I, and k is the smallest index, such that tth coordinate of A is 0 if t greater than k. As the tth coordinate of A is 0 for all for all t greater than k. So after k you have everything to be 0. Now what? This will implies that 2k times a is 0, right? And thus uh, a belongs to torsion of m. You pick it to be an arbitrary element, and this will imply that m is a torsion module because a was an arbitrary element. So for any arbitrary element you are getting this condition. So m is a torsion module. Now you need to prove that the annihilator is 0. Annihilator is 0. Okay. So now the other claim is annihilator of m, that is the intersection of all annihilator that is 0. Uh, uh, Annihilator, this is 0 that we need to prove. Now for that, what will we do? Just change the color. So now let R belongs to annihilator of this. Then choose K such that R is less strictly less than K. See here your ring is Z. So uh, this annihilator has to be subset of Z. So we can choose an integer which is choose an integer r k such that r is less than 2 times k. Okay, so we can choose an integer whose such that r is smaller than 2 raised to k. Now then consider this element a, which is 0 0 0. Here you have 1 plus z 2kz, and after that it has 0 everywhere. Although we don't, we can choose arbitrary anything after 1 plus 2kz, because this part won't be 0 by r, but like for the simplicity choose an element such that it is 0 everywhere except the kth at the kth coordinate. So if r belongs to intersection of, this is definitely inside your module m, r is in the intersection of all elements, then definitely R has to be inside the annihilator of this M also, this A also, and which implies that RA should be 0, but that would have implies that R plus Z by 2kz has to be 0, and that would have implies that 2k divides R. But uh, this is a contradiction to r less than 2k. Okay. Yeah, definitely we assume in the beginning we have to assume that it is a non-zero element. Okay. So mm, so for a non-zero element you will get a contradiction, so this will implies that r is not inside uh, annihilator of a, which implies that annihilator of intersection of all annihilators is going to be 0. Okay, this is an example for which the given condition doesn't hold, so b is false. So you have a is true but b is false. Oh, sorry. We need to find an example, right? Such that this condition holds. So we find an example such that annihilator of m is intersection of annihilator of m is 0 and m is equal to torsion of m. So B is also correct, right? Here we just need to find an example. So we have found such an example. Yeah. So yeah, let's move on to the next question and the last question of this for today's discussion. Just give me some seconds to copy the question. So here it is. It says that an R module is called irreducible if uh, M is non-zero and 0 and M are the only submodules of M. So consider the following two statements: that M is irreducible, then M is generated by a single element, some single non-zero element, of course, because if M is 0, small m is 0, then N will become 0. So definitely this condition is for that, so that your M is non-zero. So it is generated by a single element. Second, it says that if M is generated by a single element, then M is irreducible. We need to see that which of the statement is correct. So let's check the first part. A, it's a and let M is irreducible, and this is definitely, as we are assuming it to be irreducible, it has to be non-zero. That has and you pick any non-zero element inside uh, and m0 belongs to m. Then the module R of m, which is Rm such that R belongs to R. This module is definitely uh, is a submodule of M, because M is a module and small m is there. Submodule of M. Okay, since M is irreducible, so any submodule of it, since M is irreducible, 0 and M has to, the only some modules are 0 and M. Since M is irreducible, uh, either Rm is 0 or Rm is M. So see, here in the assumption, we should assume that R is a mm, uh, unitary ring. It must have uh, one inside it. Otherwise, you can just pick the zero ring. For zero ring, this is going to be happen. Okay, so I'm just writing here we are assuming, yeah, we are working with unitary rings only. So 1 dot m, that is m is inside your rm. This will implies that rm cannot be a zero module, and thus rm has to be m, and hence the a statement is true that uh, you have rm to be m. Now for b pick r to be z, so and m to be z. When z is, you can see that z is just 1 dot z, right? It's generated by 1, or z dot 1, you can better to write z dot 1. 1 is non-zero, but is m irreducible? No, because there are many submodules of it. 1, right? So let me just change the color. And for each n belongs to z, and z is a submodule of m. So this implies m is not reducible. M is not irreducible. So B is false. A is true, but B is false. So that is there. So A is true, but B is false. That should be the answer. So I will stop here. Uh, I will meet you guys again in the next live interaction session with the assignment number 11. Please do attend Shubhajit's lecture also. He will solve the next 7 questions. Okay then. Thank you.